In this question, we're given a utility function, which is in Cobb-Douglas form, which I'll talk about in a sec. And we're given some information about the person's income and the prices that they face. And we want to find the optimal consumption bundle. So in general, for these types of problems, when your utility function is Cobb-Douglas, which again I'll explain in a moment, there actually is a shortcut for how do you answer questions like this. So I'll show it to you the normal way of how you should do a problem like this to show all your work and get full credit and really understand it. But then, as kind of a little check at the end, I'll also show you the shortcut for how you can interpret this utility function and how you can kind of get the answer in a slightly different way. That said, before we proceed, let me talk a little bit about utility functions in general. There are different types of utility functions, and depending on that type, there's actually a different strategy for how to go about solving for the optimal solution. So this is Cobb-Douglas. Cobb-Douglas is anything in the form where you have good 1 to some exponent times good 2 y to some exponent. Usually these exponents add up to 1. So in this case, 0.25 and 0.75. And C and B are just the two different goods names. This is like good X, which is coffee, and then Y, good B, is books, right? So, but in general, anytime you have something like this, your utility is the product of the two goods that you're consuming, each raised to an exponent. And again, usually they add up to 1. They don't necessarily have to. But that's a Cobb-Douglas thing. And as we'll see for Cobb-Douglas, the strategy is mostly gonna be to go about this the normal way, which is to set MRS equal to price ratio, which I'll explain more in a sec as well, in case you need a refresher. But for other utility functions, specifically if your utility function is a perfect substitutes, if the two goods are perfect substitutes, you know that that's the case when it's perfectly linear. So if instead of like this, if your utility is like ax plus by, the two goods aren't multiplied, but rather it's like a linear function added, just some slope times your good 1 plus some slope times good 2. That's when the two goods are actually perfect substitutes with each other. And then there's a different strategy for how do you go about optimizing. And similarly, if the two goods are complements, kind of like, like left shoe and right shoe, you kind of want to buy them in a pair together. If they're complements, they kind of go together. In that case, your utility function would look something like minimum of good 1 and good 2. And so if it's perfect complements, there's a different strategy yet to go about how do you optimize it. So for these two, there will be problems that follow involving those. So, we can go through the solutions for those there. But for now, just in general, thinking about Cobb-Douglas, but also even if you don't know much else about the utility function in general, the way to go about optimizing is first to figure out what's your budget constraint, right? What's a constraint in the world that we have? So let's see. In general, the equation for a budget constraint, we could think about it as this equation. P1x1 plus P2x2 equals M. This is basically saying, all right, well, let's see. And we can apply it to this context specifically. So instead of x1 and x2, I'll call it, C and B. So C is our x-axis good. B is our y-axis good. So here, overall, first of all, we know that you're spending $5 on coffee, each cup of coffee. So let's say C is the number of cups of coffee that you're getting. Well, then 5 times C, that's the number of dollars that you're spending on coffee. $5 a cup times C cups, that's how much money you've spent on coffee. Plus, for books, it's $20 each. So $20 times the number of books that you've bought B, that's how many dollars you've spent on books. If you add them up, that's how much total money you have to spend. And if your income is $400, assuming you have to spend it all, there's no such thing as savings in this world, that needs to add up to $400. So this is a budget constraint. And if you graph this budget constraint, it looks something like this, where if this is the number of cups of coffee you can buy, this is the number of books you can buy. It's going to look something like this, where if you were to spend, for example, all of your money on books, you could buy, what's that? 400 divided by 20 is 20. So that's 20 books. And then if you do 400 divided by 5, that's 80. So that's like saying, all right, just you don't even need this equation to know that. If I just said, hey, if you have 400 bucks and you spent them all on coffee and it's $5 each cup of coffee, then you know that you could buy 80 cups of coffee. And so if you were to do that, you have $0 left for books. So 80 comma 0 is a consumption possibility for you. If you buy 80 cups of coffee, you'll have 0 books left to buy on books. And similarly, if you spend no money on coffee, then you can buy up to 20 books. So you're allowed to consume anything on this green line connecting these 2 points, right? So the more coffee you want, the fewer books you can buy, and so on. If you were to consume any bundle, any XY coordinate point within this, then you're leaving money on the table. You're not spending the full $400. And any point in this part of the plane is costing more than $400, so you can't afford it. So to spend exactly $400 means to be exactly somewhere on this line, connecting 20 books with no coffee with 80 coffees and 0 books. So any linear combination of them, there's many points on them, is representing that you're spending exactly $400. So this is going to be true for all people in the world. Now, what's specific to you in this situation is your utility function. So really, utility, the optimization, this whole process comes from merging 2 very different things. One thing being, what's a set of things that anyone can afford in this context? So anyone who has $400 and faces these market prices can afford this. To combine that with, what do I like? And the utility function is really describing mathematically what you like and the trade-off between how much you like more of one good versus the other and things like that. So in general, the utility function, you can watch the previous videos to look at what an indifference curve is, but any utility function is going to have indifference curves. You could then think about that as, if I were to set the utility to a specific value, then now there's only 2 unknowns in this equation. It's only x and y, or again, in this case, c and b are the only unknowns. If I were to plug in a specific number for utility, like if my utility was equal to 8 or something, then you could figure out how many c and b, what combination of c and b gets you exactly 8 utils of happiness. And so each of these are for a specific utility level. So this is just giving you what are all the different bundles of books and coffee that get you exactly a certain number of units of happiness. And the long story short point is that the optimal, there's infinitely many, indifference curves. So here you're indifferent between all the points on any one of these red lines because they all give you the same amount of utility as each other, whatever you had set it to. So and again, there's infinitely many indifference curves. The optimal point is specifically referring to the one indifference curve that's perfectly tangent. So there's many indifference curves, but there's only going to be one indifference curve where it's perfectly tangent at some point to the budget line that we just drew, this equation that we just drew. And so basically, long story short, the math that you would normally do to solve for that optimal point involves 2 things. One, we want to be on the budget line somewhere, so we're going to have this equation's got to be true. The other thing that's got to be true is that the slope of this red indifference curve has to match the slope of this green budget line. So that's what it means to be tangent. It means that the slopes are the same. If you zoom in, the steepness of the red and the green are exactly equal at that optimal point. So long story short, we're looking for 2 conditions to be true. One, that this budget constraint holds. Great, that's easy enough. Second, that the MRS, which is the slope of the red indifference curve, which we'll use calculus to solve in a sec, needs to equal the slope of the green budget line, which is always given by the price ratio, P1 over P2. And technically speaking, the slope of the MRS, it's always a negative slope. The budget constraint's always a negative slope. And so really, there's technically a negative in front of each of these, but setting them equal to each other, you kind of don't even need the negative. So long story short, what you want to set equal is this. The MRS, the slope of this red indifference curve is always going to be the derivative of utility with respect to good 1 divided by the derivative of utility with respect to good 2. And again, I'm just going to ignore the negative sign because you could drop it from the right-hand side as well. So that ratio, which is the MRS, needs to equal the price ratio P1 over P2, which again, that's just because if you were to look at the slope of this green line, that's just going to, if you were to solve for B, the y-axis good, and the sum x plus b, this ratio is going to always be P1 over P2. So the x-axis goods slope price over the y-axis goods price. So long story short, this ratio over here, this is what we're looking for. So let's now apply that to this problem here. So the derivative, so first actually putting it in context for us, we're looking now for the derivative of the utility with respect to good x, which is c, over the derivative of utility with respect to the y-axis good b. That needs to equal the price of the x-axis good, which is c, which is 5. Price of coffee was 5, over the price of the y-axis good, books, which is 20. Now, notice philosophically here, we didn't really specify which is the x-axis good, which is the y-axis good. I just kind of assumed that the first letter I saw was the x-axis good, c. But philosophically, it doesn't matter if you were to switch those as long as you're consistent. So if you treated, good 1 as books, then that's fine. You would just have 20 on top here, but then you'd have this derivative on the numerator there, and so the ratio, it's going to be the same. So it doesn't matter what you do as long as you're consistent. So here, derivative with respect to coffees on the numerator here, price of coffees on the numerator here, derivative with respect to books is denominator here, price of books is denominator there. So we're going to set this ratio equal to each other, and now it's just a matter of algebra between doing this equation. So now we're going to have a system of equations where one equation is this. The other equation is just our budget constraint because we got to be somewhere on that green line. Again, big picture, got to be tangent. That's what we're doing here. This is called the tangency condition. That's got to be met. And then we've got to be somewhere on the budget line, this green equation. And so once we have those two, that's going to give us a unique point in space, and that's the optimal bundle. So here, let's just do this math now. So the utility function here is u equals c to the 0.25, c to the 0.25 times b to the 0.75. So let's now find what is the derivative with respect to c. Well, the way to take derivatives is just to, here the key is that this b to the 0.75, that's treated like a constant because that's not your variable c. So it's kind of like if I were to ask you what's the derivative of 5x squared, you're going to treat the 5 as a constant, which means it stays there. And then you just bring the 2 down. So it's 2 times the 5x to the, and then you reduce this by 1 to the 1. That's how you were to take the derivative. So it's going to be the same thing here. Here the b plays the same role that the 5 does. So here we're going to treat this like a constant that stays there. So imagine this is like the 5. And so the derivative here, the derivative with respect to c, so this b to the 0.75 just kind of stays there. So it's really, this is like the main show, c to the power of 0.25. So the derivative of that's going to be 0.25 comes down times c to the power of this minus 1, so negative 0.75. Because that's how you take derivatives. You take the exponent down and then reduce it by 1. So the 0.25 came down, we subtracted 1, so it became negative. And anything that was multiplied that doesn't have your variable c just stays there for the ride. It's just a constant. And similarly, the derivative with respect to b, what'll go into the denominator here. Here, I'll just erase this. So the derivative now, if b is your variable, now this in fact is the constant that stays there, c to the 0.25. And so then the derivative of this, the main part of it is 0.75 coming down times b to the, when you subtract 1 from 0.75, you get negative 0.25. All right, so now that we have all that, let's see. We can set it up as this first guy divided by the second guy. So just copying just to get this ratio. So we could say this. I'm just going to put this over here. I'm going to put this 0.25 first now. So this is 0.25 times, just to be consistent, I'm going to put the c first. So c to the 0.75, negative 0.75, times b to the positive 0.75. So again, this is the same thing as this. I just reordered them, but it's just multiplication. Divided by this, which is same thing, 0.75, and then c to the 0.25, b to the negative 0.25. So all this is just the ratio over here. I can uncircle this now, but so yeah. So we have that, and now we need to set that equal to just the price ratio, which was 5/20. And again, this looks more complicated, like, oh man, how are we going to do this math? But things will cancel out pretty nicely here. So I'm going to just copy this. And now let's think about how we could simplify this. There's a c on the top and the bottom. Now, in general, whenever just to recap some math, if you have x to the 20 over x to the 13, the way you do this is you would just subtract 20 minus 13 and say that's x to the 7th. It's like there's 20 x's multiplied here, 13 on the bottom, so you just subtract to get x to the 7th over there. So similarly here, you could think of this as this is this minus this, so you could think of this as really having c to the negative 0.75 minus another 0.25, which is just c to the negative 1 on top. And again, there's like a 0.25 over here, 0.75 here. And then same with the b's. You have b to the 0.75. You're going to subtract this denominator. So you have 0.75 and then minus the negative 0.25, which is really plus 0.25. So it's really b to the positive 1 over here. So long story short, looking at the c's and the b's, here you have this, if you just take the top minus the bottom as far as exponents go, you get negative 1 for the c and positive 1 for the b. And what that means is for the c, you could also think of this as just the c being on the denominator, because x to the negative 1 in general is just 1 over x. So here the c to the negative 1, you could think of that as just being c on the bottom. And alternatively, if you prefer, you could just think of this as being 0.25 minus this negative 0.75. Same thing, that's just going to be a c on the bottom. So in either case, this whole complicated looking left-hand side just ended up simplifying to 0.25b over 0.75c. And we're just going to set that equal to 5/20. And so now we could just cross multiply to get the math. If we cross multiply both sides, we could multiply 0.75c and 20. So this side ends up being 0.25. Yes, like this and then this, right? So we're just going to say 20 times 0.25b equals 5 times 0.75c. And so 20 times 0.25 ends up on my calculator being 5b equals, and then 5 times 0.75 on my calculator ends up being 3.75. So we get this. All right, so we basically get some sort of ratio, setting them equal. And so, and you could, if you wanted to, you could, for example, divide both sides by 5 to get b is whatever 3.75 over 5 is, like that times c. So we have this, and then the other thing that's true is the budget constraint, which is 5c plus 20b equals 400. So 5c plus 20b equals 400. So with this, we could then plug in, oh yeah, and this, by the way, on your calculator would simplify to 0.75. So 3.75 over 5 is just 0.75. So we could basically rewrite this as saying b equals 0.75c, which will make it easier to plug in. So when we do plug it in, we see that we can replace this b with what it is, the 0.75c, which means this equation becomes 5c plus 20b, which is, again, really 0.75c, equals 400. And then now it's just simple algebra from there. This is going to be 5c plus, and then this product is 15c. So 20 times 0.75, that is 15. And now when we add this, 5c plus 15c is 20c equals 400. Divide by 20, and you get 400 divided by 20 is 20. So you get c is 20. And for b, you don't necessarily need to do all this math like this. We already knew that b was 0.75c. So b is going to be 0.75 times c, which is 20. And that's 15. 0.75 times 20 is 15. So our final answer is that your optimal bundle is B is 15, C is 20. And now looking at the original budget constraint over here, we have 20 coffees over here and 15 books over here. Again, you could verify that that's somewhere on your budget constraint, that this costs exactly $400. Again, you could verify it that way, where if it's $5 each here, that's $100 here, and then 15 times the $20 for each book, that's $300. So we're spending $400. But let me very briefly show a little shortcut. So Cobb-Douglas, the reason why we as economists even have thought of, oh yeah, like why would we even pick this function? Well, the neat thing about this function, and we won't go into the crazy math about why this is true in general, although it's very similar to what we've done, except treating the prices instead of using 5 and 20. If we left this as P1 and P2 and did the math, it'd be a lot more abstract. But here's what we'd conclude. The conclusion is that, in fact, when you write this such that they add up to 1, this is a nice little interpretation, because that exponent is the percentage of your budget that you're going to spend on that good. And knowing that one little sentence in English literally solves the problem instantly. So here, if I just told you that if you're somebody who's going to spend 25% of your budget on coffee, you immediately know how many cups of coffee you want optimally. Because a quarter of your budget is a quarter of $400, which is $100. And $100 divided by 5 cups of coffee is 20 cups of coffee. Bam. And similarly, if you're going to spend 75% of your budget, of your $400 budget, which is $300 on books, $300 on books divided by 20 bucks each is 15 bucks, and that's exactly what we had. So notice how quick that was. So that's a little shortcut that you can use. But again, oftentimes professors want to see that you know how to solve all the steps and knowing all the calculus involved. So this video goes over all that, but also in general, if you come across something like this and you just need a quick answer, you could check your answer that way.